Hi, everyone. This is the last example from section 14.3. It's an exercise in differentiation, so partial differentiation, but it also asks us to verify that the partial derivatives of a function satisfy some relationship. In this case, the relationship is a differential equation. So we want to show that this function u satisfies the three-dimensional Laplace equation, which says that the second partial of u with respect to x plus the second partial of u with respect to y plus the second partial of u with respect to z equals 0. So in some sense, they all sort of cancel out with each other. So let's have a look at how to do this. So we're going to want to compute the second partials. So that means we're first going to take their first partial derivatives. To do that, it'd be nice if we had it in a form where we could use the power rule instead of, say, the quotient rule, at least for the first derivative. So let's go ahead and find the first partial of u with respect to x. So we're differentiating x squared plus y squared plus z squared to the -1/2. By the power rule, this is -1/2 x squared plus y squared plus z squared. And the new exponent up here is going to be -3/2. And then we multiply by the derivative of the inside, which is 2x. So this becomes -x over x squared plus y squared plus z squared to the 3/2. Now we're going to go ahead and get our second partial derivative. So that's d squared u over dx squared. That is, we want to compute the derivative of this expression with respect to x. And so for this, we're going to use the quotient rule. So it's the derivative of the top, which is -1 times the bottom, which is x squared plus y squared plus z squared to the 3/2. And then it'll be minus the top, so that's plus x, times derivative of the bottom, so that's 3/2 x squared plus y squared plus z squared to the 3/2 minus a half. So that will be, 3/2 minus 1, so that'll be a half, times the derivative of the inside, which is 2x. All of that is over the bottom squared, x squared plus y squared plus z squared cubed. And now we'll just do a little bit of cleanup. So I've got a common factor of a 2 that's happening, one on the top, one on the bottom, so those cancel out. Notice I've got the expression raised to a half, and then the expression raised to the 3/2. So that 3/2 can be written as 1 plus a half. So in other words, it's the square root of x squared plus y squared plus z squared times itself. So we can factor that out. So I'll get an x squared plus y squared plus z squared to the power of a half. Factoring that out, what does it leave in the first term? It just leaves a -x squared plus y squared plus z squared. Factoring it out from the second term leaves me with a 3x squared. And then all of that is over x squared plus y squared plus z squared cubed. And now I can take that square root on the top, that x squared plus y squared plus z squared to the 1/2, and I can cancel with a bunch of stuff on the bottom. That leaves me with an x squared plus y squared plus z squared. It would be 3 minus a half, which is 2.5, or 5/2. So that's the power in the denominator. What's left up top? What's left up top is we have 3x squared sitting there on the far right, minus an x squared. So we have a 2x squared minus a y squared minus a z squared. And so that's our second partial with respect to x. Now, if you notice that there's really a lot of symmetry here. If I do the calculation for the y partial, so the second partial derivative with respect to y, basically everything's going to be the same, except I've just switched the role of x and y, if you will, due to symmetry of the original function, the x squared plus y squared plus z squared. So we don't have to go through the calculation. We can just note that similarly, I got to make sure that it's the square on the d in the top, and then it's on the y on the bottom, the dx or the dy on the bottom, because that's what's being differentiated with respect to twice. So this is going to be the same expression, except the roles of the x and the y have been reversed. So this would be a negative x squared plus a 2y squared minus a z squared all over x squared plus y squared plus z squared to the 5/2. And the second derivative with respect to z is going to be the same thing, except now it's the z that has the 2 in front of it. So minus y squared plus 2z squared all over x squared plus y squared plus z squared. So in other words, we noticed some similarity, some symmetry here, so we could save ourselves some calculation. And therefore, we've now got our partial derivatives all expressed. So when I take the second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z, what am I adding up? I'm adding up this and this and this. And so what do we get? We get the same denominator for all of them. X squared plus y squared plus z squared to the 5/2. And what's up top? Well, we have a 2x squared and then a minus 2x squared. The minus 2x squared is coming from, there's a minus x squared in the derivative with respect to y and a minus x squared with the derivative with respect to z. And then we also get a plus a 2y squared minus a 2y squared plus a 2z squared minus a 2z squared. And so we get cancellations that happen. That's 0, that's 0, that's 0. And therefore, the resulting sum is 0, which verifies what it is we wanted to verify, that this function satisfies the Laplace equation. All right, that's it for this example. Thanks for watching.